All right. So, good morning to all of you. Uh, Thank you for the introduction. I'm now, as of you now, since you know, I'm Bhavesh, and I've been working with Professor Aparna Singh as a PhD student in the Metallurgical Engineering and Material Science Department at IIT Bombay. So, since here, this here is the title of what I'll be presenting today. And this title here contains some terminology, which I'm sure that the audience here is very familiar with, while there are some terminology like this, which we'll dwell deeper into as we go along the presentation. So without further ado, first things first, I'll briefly explain what my presentation will contain. So I'll start with the motivation behind this study and the objectives that we have set using that motivation. Further, then I'll explain what the effect of heat treatment that we had done on the material called as nanostructured bainite will reveal on the effects on the mechanical and the fatigue crack growth behavior. Then moving on, we'll talk a bit about the specimen preparation that has been subjected to investigation using a transmission electron microscopy so as to provide this whole study a microstructural point of view. Then I'll explain the TEM results that are there using that investigation. And finally, I'll conclude my whole presentation so that once we leave the room, we have developed a better understanding of this fascinating material. So, I'll start with the introduction of what nanostructured bainite is, though it was given by Professor Morales as well, but just for the sake of this presentation. So, nanostructured bainite nanostructured bainite actually possesses very high mechanical strength and along with satisfactory ductility. So that strength goes in orders of magnitude of about 2 GPa. So this superior mechanical strength and the very well established ductility as well, these both are attributed to the nanometric scale of the microstructure that it possesses. So there are two primary microstructural constituents which are called bainitic ferrite, and then there is another microstructural constituent known as retained austenite. So once we examine that microstructure using a scanning electron microscope by etching the sample using a 2-weight% nitrile solution that works perfectly well, we observe that most of the bainitic ferrite gets etched away, and what remains is the two different morphologies of retained austenite. So first morphology is known as the film type austenite, which is this very fine layer of austenite. And then there is these chunks of or retained austenite, which are known as the blocky type retained austenite. These are undesirable yet unavoidable because these blocky austenite, they transform into martensite upon earlier stages of deformation. And as a result of that, there is undesirability of this because these render the steel embrittle. So now, since we know a bit about what nanostructured bainite is, I'd like to point out that once we reduce the length scale, there is an enhancement of strength of the material, but it comes at the expense of the ductility and the toughness. So in such a cases, there are several applications such as railways or other structural applications where this material shows good applicability. But there may be times when these materials has to be subjected to fatigue loading. So the phenomena behind this effect of refinement on the fatigue behavior of this steel from a microstructural point of view is not yet completely understood. So as a result of that, we decided to analyze the fatigue crack growth rate tested specimen using a transmission electron microscope to dwell deeper into the phenomena that is underlying or that is hidden behind this effect of refinement that is taking place. So for that, we prepared a steel having this chemical composition using a vacuum induction furnace. And after the steel was cast, we homogenized it at 1000 degrees Celsius for 48 hours. And this was then subjected to hot rolling at 1000 degrees Celsius in subsequent passes. Once the rolled steel block was there, we parted it in two blocks. So both the steel blocks were then austenitized at 950 degrees Celsius for 40 minutes, like this. And then we austempered it or isothermally transformed it, transform one of the blocks at 250 degrees Celsius and another block at 350 degrees Celsius for 40 and 20 hours respectively. So these are the corresponding microstructures that we obtain for the two heat treatment conditions. So as observed from the TM images, we saw that the specimen that was austempered at a lower temperature, hereby labeled as NSB 250, showed dominance of the ferritic laths, while this specimen, which was austempered at a higher temperature, had higher proportions of austenite present in that. So in order to confirm that theory, we tried analyzing the data obtained through X-ray diffraction and determined the volume percentage of ferrite and austenite in both the cases. So we observed that specimen austempered at a lower temperature had higher proportions of benitic ferrite as compared to the specimen austempered at higher temperature, and vice versa for the retained austenite case. We also tried determining the benitic lath thickness using multiple SEM images and observed that the specimen austempered at a lower temperature showed finer benitic lath thickness as well as retained austenite thickness as compared to specimen austenite austempered at higher austempering temperature. So now let's look at what this refinement has done to the mechanical properties. So as observed from the mechanical properties, the specimen that was austempered at a lower temperature shows higher values of yield strength and UTS as compared to the specimen austempered at a higher temperature. But the elongation and the toughness trends say otherwise. So we have a higher elongation and toughness for the specimen that was austempered at a higher temperature. Now, this was attributed to the higher proportions of softer retained austenite phase present in the higher austempered specimen as compared to the stronger or the harder benitic ferrite phase, which mostly contributes to the strength of the material, which can be seen here for the lower austempered specimen, which contains higher benitic ferrite fraction. But what we are concerned in this study has been marked in this block. So for the fatigue crack growth behavior, what my co-authors have done was they measured the delta KTH or the threshold stress intensity value using a decreasing load test, and they then plotted the region 2 or the stable crack growth regime, which is also known as Paris law regime. And by fitting it with linear regression, they determined the quantities mentioned in this particular expression. So C here is the intercept and M here is the slope. And these values were determined for both the cases of 250 and 350. And it was concluded on the basis of these values as well, that there is a higher crack growth for lower austempered specimen as compared to the higher austempered specimen. But upon observing all this, we could also see that the delta K value for this NB250 specimen it extends up to 25 megapascal root meter, while in case of NB350 specimen, it extends up to 35 megapascal root meter, which is a significant difference here. So after considering all this, the question that comes to mind is, what is causing all of this? Which microstructural feature or phenomena is behind this type of behavior of these steels? So we tried to examine the microstructure that was there in the Paris law regime specimen, and for that, what we had done is we took the fractured half of the CT specimen that was fatigue crack growth rate tested, and upon measuring the length where we could find a region in which the Paris law regime was evident, we extracted a specimen out of that particular portion using a focused ion beam milling. And that lamella sample, which was produced using a focused ion beam milling, was then subjected to transmission electron microscopy examination. So moving on to the results, these figures are here for the 350 specimen that was austempered at a higher temperature. So what we could observe was there was significant transformation of retained austenite into martensite. But apart from that, we could also observe that the austenite had undergone some deformation twinning. And this is in addition to what the prevalent theory currently is. So it is recommended that when when the crack tip, when there is plastic zone of crack tip, it approaches the retained austenite fraction, the retained austenite fraction develops some compressive stresses at the crack tip because it is undergoing volume expansion due to martensitic transformation. As a result of that, that crack tip closes slightly, and thus there is resistance to the crack growth. That is why we were looking at those figures where the delta KTH value as well as the delta K value for NB350 specimens were higher. But this is the prevalent theory which does not take into account the formation of deformation twins, only the transformation of retained austenite to martensite. So there might be an additional factor in terms of this deformation twins, which is also absorbing the mechanical input energy, and as a result of that, resisting the crack growth. But let's not get ahead of ourselves and look at what the other sample, which does not have high amount of retained austenite, has to offer. So this here is the TEM imaging, which we observed for the specimen that is having a higher bainitic ferrite fraction. So we observed that the bainitic ferrite that was present had undergone significant deformation with presence of heavy dislocation network inside and around the bainitic lens. Further, in the austenite, we could observe that there is a formation of microtwins. This is not yet completely developed into a deformation twin, but only microtwins were present, which suggests us quite a few things. So first of them would be that whatever dominant microstructural feature is present will determine the fatigue crack growth characteristics of that particular specimen. Secondly, we have here that presence of bainitic ferrite does not help much with the crack growth resistance since it gets heavily deformed and can be evident from this whole dislocation network that is present. Thirdly, coarser retained austenite is much better in resisting the crack growth as compared to finer bainitic ferrite, but finer retained austenite, because because we could observe some deformation twins forming in those retained austenite features, while here finer retained austenite does not allow for formation of deformation twins and is not actually absorbing that much energy from the input mechanical energy. So as a result of that, we could come to the conclusions that once we have a higher austempering temperature, there will be lower proportions of bainitic ferrite and there will be increased proportions of retained austenite. That increased proportions of retained austenite, they will result in enhancement of ductility and toughness, while this increased proportions of bainitic ferrite will lead in enhancement of mechanical strength. Further, in addition to the prevalent theory of transformation of retained austenite into martensite upon deformation, there is another factor, which is the introduction of deformation twins that is also accompanying the transformation of this retained austenite to martensite in order to resist the crack growth in such a sample. And for the last conclusion, the samples which had lower proportions of retained austenite in them, the harder bainitic ferrite phase, it underwent severe deformations in the early stages only, and thereby the crack growth does not reach to high levels of delta K and immediately goes into the catastrophic regime of failure. So I'd like to thank all of you for listening to this presentation. This here is a 3D representation of what bainitic microstructure looks like. It's not corresponding to the microstructural length scale, as I just made it so because it looked interesting to me to observe everything beyond 2D for something. Thank you.